In this unit has split off into two major categories, solutions and equilibrium category. We've covered considerable amount of the solution category, and now we're hitting the equilibrium portion. Within the equilibrium portion, we involve both solute, solvent, and solution, and we discussed a little bit about reversible and forward reaction rate. Now our focus will be on quantifying the product and the reactant in ratio format. So here's what I mean. A reaction of a quotient of a homogeneous reaction. What does all that mean? Well, say you have a reaction in which A and B, they're both gases, forming into C and D, and they're both gases. Now, these M, N, X, and Y, they are the coefficient, meaning the value that is in front of a balanced equation. In order to do a ratio between the product and the reactant, we utilize this particular equation, in which we have the product concentration on top, and we have an exponent that is represented in the coefficient, and then same here, the reactant is on the bottom. Now this right here equation is, you see that QC is called the reaction quotient. The reaction quotient shows the relationship between the product over the reactant at a particular point in time, except at equilibrium. So any part in the beginning, a little bit towards the middle, or towards the after equilibrium has passed and now it's going reverse direction. So the QC, or the reaction quotient, really is all about any point in reaction is taking place except at equilibrium. Let's go dive a little further into this equation and to kind of illustrate and put in values to get you to a value of a reaction quotient. So I have mentioned that these C and D, that's the product, remains on the numerator. And on the numerator, these are brackets. These brackets represents that these are in concentration of molarity. And same for the reactant. This X, Y, and N, that represents the exponents, and that comes from the coefficient of the balance equation. So the numerator, the product concentration are on the numerator, the reactant concentration are on the denominator, and they're multiplied together, top and then the bottom. And then each concentration is raised to the power of the coefficient of balance equation. Also note that these are all gases and all, or it could be aqueous species, and to put these kind of values in a reaction quotient equation. Let's do a learning check. It says write concentration-based reaction quotient expression for the following reaction. So I'm going to do B, you try A and C. So B, I'm going to go ahead and put QC is equal to, I have my product, which is NH3. So bracket NH3 to the what power? Second power, since the coefficient is in second power. Then I'm going to go ahead and put a division sign, because on the denominator we have N2, and that's to the first power, and then H2 to the third power. You don't have to write the 1, so we can write it like this. That's up to you. Now you try A and C and come back. And here is the key. Moving along, let's do another learning check. And this requires putting in some values. So if the concentration of NH3 is 1.10, H2 is 0.88 molarity, and H2 is 0.75 molarity at a particular point in time, what is the value of the reaction quotient? Reaction quotient is written as follows, where we have concentration of the product to the second power, since that's the coefficient, and we have N2 and H2 to the third power. Now, the value of the NH3 is 1.10, so we're going to just plug that in, 1.10 to the second power. And these are all in molarity, so it fits very well. 8 molarity. And then we have 0.75 to the third power. So let's plug this into the calculator very carefully, utilizing some parentheses. First, we're going to work on the numerator, which is a 1.10, and then that's to the second power. And I'm going to hit enter. That's 1.21. Then let's work on the denominator. Note that there is 0.88 and a 0.75. So you want to use double parentheses. In that, first, we're going to go ahead and put in 0.88. And then you're going to go ahead and put another value, 0.75, and that's to the third power. And then double parentheses. So note that there's a parentheses here, parentheses that's to encapsulate the 0.88, and another parentheses to encapsulate the 0.75, and there is a most outer parentheses in order to parenthesize everything. Okay. And I get the value of 3.3. And that's value of the QC, or the reaction quotient. So far we've been looking at homogeneous reaction, in that they were all gases, okay, or it could have been all aqueous species. What about if we have a reaction quotient for a heterogeneous reaction, in which we have a combination of a gas and a solid and even a liquid? In this scenario, the reaction quotient does not include solid and liquid. It only includes the gas and the aqueous. So look over here, you don't see the D, you don't see the B on the reactant side, and so you only see the C and the A, in which they're both gases. So we don't include the solid or the liquid to determine the reaction quotient. So let's do a learning check. It says, what is the reaction quotient expression for the decomposition of calcium carbonate? So here you see this is a heterogeneous reaction, and so therefore you're going to have to distinguish which one is a gas and a non-gas substance here. So the reaction quotient, or QC, is equal to the product. In the product side, we just have the carbon dioxide gas as the product in which it incorporates into the reaction quotient, not the calcium oxide since it's solid. What about on the reactant? This is also solid too, so we don't put that there. So QC is actually equal to the concentration of the carbon dioxide, and since these are all 1-to-1 ratio in terms of balance equation, we just leave it as is. So now you're going to try this particular learning check, come back and check the key. And here is the key. One note that the reaction quotient do not have a unit.